Alright, Assalamualaikum warahmatullahi wabarakatuh. Today I'm going to be presenting about question 5 for Lab 1 module for perimeter calculation of 10 squares for the topic branch, loop, and subroutine for assembly language programming. I'm HAZEEM HAZRI, student ID 2025486756 from group CEE 22224A. So the address question for question 5 is to construct an assembly program to calculate perimeter of 10 squares and assume the length of side of each square is an 8-bit hexadecimal number stored in memory location starting at 0x20000040. If the perimeter of a square is more than or equal to 0xff, subtract the result with 0x20 and store it in register R8. If otherwise, add the result with 0x10 and store it in register R9. So the given data is square stand, data size 8-bit each, start address is 0x20000040, threshold perimeter more than or equals to 0xff. If more than or equal to threshold 0x20 is R8. If less threshold, it's plus 0x10, it's to R9. Here is the objective of the question. First is to apply loop techniques, which we can construct an ARM assembly loop that processes 10 subsequential 8-bit values in memory using a loop counter and pointer register. Second objective is that we want to apply conditional branching. We use the CMP and conditional branch instruction, BHS, which we can select between two arithmetic outcomes based on the perimeter value, following the table's one branch condition. Third objective is that we want to translate a flowchart into the code. We want to design a flowchart for the perimeter problem and implement it faithfully as working ARM assembly instructions. And lastly, we verify with the CPU simulator. We assemble single step and examine registers R0 until R4, R8, and R9, and memory to confirm the program behave as designed. So here is the flowchart for question 5. So from the start is the entry point for the program, and then we go to the initialize. So before the loop start, we set up 3 register, R0 as a pointer to the first length, value at 0x20000040, R1 as our loop counter set to 10 since we have 10 squares, and R2 as the constants 4 because perimeter equals to side of 4. And then it will go to load and compute. So the loop starts here. We load 1 byte and the current square side length into R3, then multiply it by R2 to get the perimeter stored in R4. And then we go to the decision diamond, which is R4 more or equals to 0xff. This is the conditional check, the module that is testing on us. So we're gonna compare the parameter 0xff, that CMP instructions set to carry flag, and VHS, branch if higher or same. So it read the flags to decide which part to take. So this is exactly the BCC pattern from table 1 in the lab module. So if it's yes, it will go to the R9 equals to R4 plus 0x10. So if the parameter is greater than 0xff, it will go to yes, and if it less, it will go to no. And then it's gonna merge into the updated pointer and counter. So both paths will join back together here. You will move to the R0 to the next byte in the memory, and the decrement R1 our loop counter. And lastly, it will go to the decision diamond R1 is equals to 0. So this is the loop exit, which subs update the zero flag when it decrements R1, and BNE check the flag. If R1 isn't 0, we branch back up the load and compute step and repeat with the next square. And then it will loop back. So the loop back is the arrow. This arrow is the actual loop back. It what makes the repeating structure instead of straight up line up program. So and then we're gonna go to end. So here is the whole assembly ARM assembly program. Um, you can see from global start until stop. I'm gonna be explaining the code for the program. So first part we have part 1, start with underscore start, and then we have LDR R0 equals to 0x20000040. So here it will load the starting address of the site length array to R0, which act as a moving pointer through the memory. And then we have MOV R1 comma hashtag 10. So here it will set the loop counter. The program will repeat exactly 10 times once per square. And then we have MOV R2 hashtag 4, which will store the constant multiplier used later to convert a site length into a parameter, which site x4. Next, we will go to the next part, which is step 2. It will load site length and compute the parameter. So after loop, we're gonna go to LDRB R3 comma R0. So here it will load only 1 byte from the memory, matching the 8-bit size of each site length value. And then it will go to MUL R4 R3 R2. Here it will multiplies the site length by 4, giving the perimeter of the current square in R4. And then here we go to CMP R4 hashtag 0xFF. Here we'll compare the parameter against the threshold and update the carry flag, which the next instruction read. Next we go to step 3, which is the conditional branch and store result. Here BHS, for the BHS part, if its branch if higher or same, it will check the carry flag set by the CMP, the same condition as BCS and BHS in table 1 of the module. And then we go to the parameter below 0xFF. If the execution falls through, R9 will equal to parameter plus 0x10, then it jumps past the greater equal block with B next. Lastly, we have the if the parameter is more or equals to 0xFF, the branch is taken to greater underscore equal, where the R8 will equals to the parameter 0x20. So for the last part, for loop control and program end, for the code ADD R0 hashtag 1, it will advances the pointer by 1 byte, so the next iteration reach the next square site length. And then we have SUBS R1 R1 hashtag 1, the decrement the counter and update the 0 flag as a side effect. And then we go to BNE loop, which repeats the process while R1 is not equals to 0. Once all 10 squares are processed, execution falls into stop, an infinite loop marking the end of the program in the CPU later. So now I'm gonna go to demonstrate the CPU later. So first of all, we're gonna put all the code inside the CPU later, and we're gonna compile and load. After that, we're gonna step into. Here I already stepped into the LDR, where it will first we gotta step into. Sorry, wait. So we're gonna step into, and we can see that the LDR R0 will point out R0 now hold the base address. And then I'm gonna step into, oh sorry, I skipped the LDR R0 PC hashtag 48. So on that part, it will confirm counter and multiple R set. And then we're gonna step into again. We go to MOVR24. Here it will here it will oh sorry, here it will confirm counter and multiplier are set. And then we go to LDRB. Here it will show R3 now holds the byte from memory at R0 at R0's current address, which will point at the memory panel to confirm it matches. And then we go to MUL R4 R3 R2. Here it will equals to the perimeter. Then we step into the CMP. So in here it will point at the carry flag, which is the status register. So this is what decides the branch. And then we're gonna step into again. In the BCS, it will show whether it is jump or fall through, matching the carry flag. And then we go to sub. So in sub, it will show the R9 or R8 value updated. And then we go to add, which will also it will show the R9 or R8 value updated. And then we go to subs. Here, after the add R0 hashtag 1, it will show that R0 incrementing and R1 decrementing, and the 0 flag flipping when R1 hits 0. And then lastly, we go to the BNE loop. Here it will show looping back to the PC. It will jumps to loop until R1 reaches to 0. So it will loop until the R1 equals to 0, which will be a lot of time. And lastly, it will, once the R1 falls to 0, it will stop and the PC will stop looping. The program will stop looping. So now we go to discussion. So the core technique is demonstrated is that it will combine all three models concept in one routine, which is the BNE, the CMP, and the BHS, and also the LDRB. And then we have the design limitation. So R8 and R9 are single registers, so each new result overrides the previous one, and the outcome of the last square process is retained. So this will store the results in memory array, which will give complete record for all 10 squares. And then we have the LDRB methods. So here, it will tell you why LDRB matters. So here, each side length is only 8 bits. So using LDRB and not LDR was essential. So a full word load will have put 3 unrelated neighboring bytes. The fourth, we have verifying flags in simulator. Single stepping confirm the carry flag toggle correctly after each CMP, which is what actually decides whether BHS is taken or not. And lastly, we have common sources of error, which is likely mistakes include using LDR instead of LDRB, mismatch in immediate values, which is either 0xFF, 0x20, or 0x10. So it will forget that subs. So 0 flag never updates, and BNE will loops forever. So conclusion of this lab 1 question 5 is that the experiment will reinforce how branch instructor BCC loop structures and arithmetic logical values operation combine to build complete ARM assembly routine. Working through question 5, it will concretely shows that flowchart decision making maps into CMP BCC pair and how condition flags like carry or zero actually drive a program flow rather than being an abstract detail. Third is that the exercise highlight the importance of matching the data, which is LDRB versus LDR. The detail is easy to overlook but breaks the program easily. These fundamentals, branching, looping, and flag-driven decisions are the building blocks of the subroutine techniques through the stacks, which will let future programs stay modular and use memory more efficiently. Lastly, for future development, storing each square's result to memory instead of the last value of R8 or I9 will make the program's output more complete and easier to verify. Here's the references, and that's all from me. Thank you.